So for this video, we're up to lesson 6 for chapter 1 for Physics 12. And in the last one, we kind of reviewed dynamics and kinematics, but we kept friction out of the stories. And now we're going to just add friction to the stories and just, again, review some kinematics and some dynamics. Still working out of that booklet for one more page where you can fill all the notes in. And here we go. First thing I want to let you know about friction, just not letting you know because you already know this from Physics 11, is that there are two kinds of friction. There's friction that happens when objects are stopped and get kind of stuck to the ground, like a couch that's stuck in the carpet after people have been sitting on it for weeks. And then there's kinetic friction when you're actually moving the couch across the carpet, and it's not quite as serious as it can be if it's stuck to the carpet. What's interesting, and the reason why we have these next 2 pages of notes, is that you've actually got one equation that can actually do 2 totally different things. And I just want to demonstrate that with our little fictitious small dog of physics here. And we'll throw some numbers out there. Let's say this dog has a mass of 15 kilograms and a static coefficient of friction of 0.4 and a kinetic, a moving one, of 0.3. These coefficients of friction, these stickiness numbers, they have no units to them at all. And if people just quote just mu equals, they're usually giving you the mu k, the moving one. Okay, but if they want to, they can overtly give you 2 separate ones, like we've got here, a mu s and a mu k. So we've only got one equation. Ff equals the stickiness number, the mu, multiplied by the compression force, the Fn, the normal force. So let's look at how you can use that in 2 different situations. And then on this first page, everything is talking about static friction. Well, we're going to start off by looking at a free body diagram for this little small dog of physics as it sits on the kitchen floor. You've got the entire Earth pulling down like a magnet, right, with this force of gravity, the weight, mg is probably how we're going to calculate it. You have the kitchen floor saying, well, I don't want to let the dog fall. I'm going to choose to push with the exact same size force back up. That's not actually in Newton's third law reaction force, by the way, right? That's just the floor saying, this seems to be like a decent thing to do. And so those 2 forces, which are totally different things, just happen to be numerically equal. That Fn creates some squish now on the dog's feet. I'm going to put a human in here pulling on this dog, trying to get the dog to go to the right. But on this page, the dog is going to be stuck, right? And its feet won't be moving at all. And that's because it's going to rely on some static friction. And I want to just highlight how you can use this equation and then what the equation can actually offer you. So the force of gravity here is going to be 15 times 9.8. It's going to be almost 150 newtons. I think it's 147. Yeah, it is, 147. Now, I never bother putting units in the middle of my work, but I put them in at the end. There should be newtons in right here after the 147, but there are no units on the 0.4. Okay, it's a dimensionless number. And when I multiply that out, I end up with this value, 58.8 newtons, right? That's what the equation says. It's right there. Ff equals 58.8 newtons. But what does that mean, right? At first glance, you might think it's saying, well, the force of friction is 58.8 newtons, but it's not true. It might be, but it doesn't have to be. This number that you calculate in the static story is actually just a warning. Okay, so I'm going to put in here, this is the maximum friction value, stuck friction value, that the dog can have before the dog's feet snap free from the ground. The actual force of friction may not be 58. Okay, the actual force of friction, that's what I mean by it. That's my pronoun there. It can vary, the force of friction, from nothing all the way up to that value of 58.8 newtons. If it doesn't need 58.8, then it won't be 58.8. So let's actually, let's look at some scenarios here just on the bottom half of this first page on what might happen depending on how hard the human pulls. You know, this F pull from a human, humans have free will, they can pull as hard as they want. The dog's humanely harnessed, so it'll be fine. And the dog's basically ready to play this tug-of-war game with you, right? The equation is kicking out this value, 58.8. Okay, well, so what? What does that mean? Well, let's put in 3 different choices for what the human does. Maybe the human decides not to pull on the leash at all, right? Or maybe they pull with 55 newtons, or maybe they pull with 60. Okay, well, what's going to happen? Well, if you only pull with 0 newtons, if you don't pull at all, you don't need any friction to stay stuck, and the force of friction value will be 0. It will not be 58.8. If you pull with 55, the friction force will be 55. So let's start penciling these in here. If you pull with 0 newtons, friction force is 0, nothing happens. If the human chooses to pull with 55, friction force is 55, nothing happens. The human, though, free will, they can pull with much force as they want, right? They can choose to say, well, I want to pull with 60 newtons, right? They're allowed to. Then what? Well, the dog can only generate up to 58.8. So if you pull with 60, that's more than the 58.8 that the dog can create. And at that point, the dog will start to accelerate. It'll snap free, right? The surfaces will kind of unbond, so to speak, and the dog will be kind of free to move. And at that point, you have to turn the page, right? This whole page that we've been working on here does not apply anymore as soon as you know that this thing is going to move. You have to recalculate. So going back, this number that you get is only a maximum warning value, okay? And as soon as you know you're exceeding that, then you have to flip the page. So let's do that. Let's look at the kinetic story. Same dog, right? Same mass, same stickiness numbers. Let's recalculate. Well, it's going to be the exact same free body diagram, of course, including the human that's pulling as hard as they want. And here's this one equation, on our formula sheet, so to speak, that we can use. And we'll use it in the kinetic story now. Very same approach, but it offers you something totally different. Now I'm going to put in that lower mu k value of 0.3, multiply it by the 147 newtons of Fn, of squish, and I get this smaller number, 44.1 newtons. That number is not a warning. If you tell me that this dog is sliding, then that is the friction force. Okay, so it's a sure thing. The sliding friction force will have that value. And it'll be pointing in a direction trying to stop this dog from sliding. It will have that value of 44.1 even if the dog is speeding up, slowing down, or even if it's cruising at a constant velocity because you're just gently dragging it across the floor. As long as that dog is sliding and as long as there's a normal force, then you're going to find you have that friction. Don't go and pull the floor out from under it, then there wouldn't be a normal force. Well, the good news is there wouldn't be friction, but the dog will fall down. We don't want to do that. Okay, bottom of the page. We have this friction value of 44.1. So let's look at some scenarios for what the human might do. Yeah, humans are interesting things. They tend to do their own thing, right? Free will. Maybe the human only pulls with 14.1 newtons. It could happen. Maybe they pull with 44.1 newtons exactly. Or maybe they pull with 89.1. Well, let's go and look at the free body diagram. We're going to have this pull force fighting this friction force. So let's go and tell the story that, right? That FNet needs to know that. So in the first scenario, you would say, okay, 14 forward in that forward direction minus 44 back is going to make this 15 kilogram dog accelerate. You end up with a negative net force, right? That's telling you that, hey, this dog is actually slowing down. You're going to get a negative 2 meters per second squared. Now remember, we said on this page the dog is already sliding. Somehow, some way, this dog is sliding. This dog won't be sliding for long because it's going to be slowing down. If you pull with exactly the same size force as friction, once this dog is going, okay, so maybe you pull with more to get it going, but once it's going, if you pull with 44, you'll find the 44 minus the 44, of course, gives you 0 net force. You'll have 0 acceleration. And that does not mean that the dog is stopped. It just means that it's not gaining speed or losing speed. And final scenario, what if you pull with 89 and the friction is 44? Well, now you've got 45 extra newtons. So now this dog is not only moving, but actually gaining some velocity. So maybe just summarizing that with some little descriptive words here. The first dog, we've already decided if it's on this piece of paper that it is moving. But it would be a dog that's moving and slowing down. Eventually it's going to stop. That middle column, that dog will just get dragged at a nice gentle speed forever. And the other column, you've actually got the dog picking up speed faster and faster and faster. Okay, well, like last day, let's look at some kind of interesting examples, right? We'll go beyond just the simple ones. Let's talk about ones that students sometimes wrestle with a little bit. The dragster one, the car one, can actually be a good one. A lot of people wrestle with this. So it says the static coefficient of friction is 0.85 for this dragster's tires. And I'm wondering what the maximum acceleration is for the dragster. And at first glance, I'm kind of thinking static. Static is stuck. How can this dragster be accelerating, right, if it's actually stuck to the road? Well, here's the neat thing about tires. as tires are spinning as you go down the road, the bottom little patch of tire is actually, if you're driving in a nice civilized way, is actually not moving compared to the road. It comes down and meets the road and then gets picked up and goes over the top of the circle again. So you actually have this little contact patch of rubber that's moving at speed 0 on your car. And you might be thinking, well, that can't be. What if I'm going 100 kilometers an hour down the road? If you're going 100 kilometers an hour down the road, the very center of the wheel, the hub, that might be going down the road at 100. The very top patches of rubber are actually going down the road at 200 kilometers an hour, but that bottom patch is actually stuck to the road. So it is actually static friction unless you spin your tires. So let's say we don't spin our tires, because it's actually better as a dragster if we don't. Let's figure out how a dragster actually works. How does it actually go, right? Well, we need to get some free body diagram action going here. We got a weight for the dragster. It's made out of stuff, so there's going to be some weight going down. The ground is going to push back up, so there's going to be a normal force on the dragster, creating some squish between the two surfaces. And now here's where it gets super cool. This is also how humans walk around, how they start and stop walking. In order to launch the dragster, using the engine and the drivetrain and the gears to get to the wheels, it tries to actually shove a patch of the road backwards. And it does it with stuck friction, hopefully, right? Like hopefully these tires are not spinning compared to the ground. And it literally tries to shove the world backwards. And you might be thinking, like, really? Is he trying to say that you get to places by shoving the world backwards? Well, you're not going to move the Earth because you're not going to notice that it moves because it's so massive. But Newton's third law says if a rubber tire tries to shove backwards on the road, then the road will shove forward on the tire. So the force we want to get into our free body diagram is this one. Don't worry about this blue one I've got here, because the whole idea of free body diagram is that you free it up in your mind, right? The dirt will be fine. Let's think about the dragster. The dragster gets shoved forward. I should have this arrow the exact same size as that blue one, because Newton's third law says it's the same size. It's going to get shoved forward by the ground using friction. And you can do your best, if you choose to, by doing static friction, because its maximum value can be bigger, well, it is bigger than the sliding value that you get. So as I stare at just the dragster, and I think about the free body diagram, I can see two forces that just kind of neutralize each other, and the overall total force is actually the friction, pointing forward. And so when I go to do F net equals ma, I'm actually going to say, oh yeah, it's friction making it go. Now, time to think about what to put in for that left-hand side. And you might think, well, it's obvious. We're just going to put in mu times Fn. Oh, be so careful. For static friction, this idea of putting in mu times Fn is only okay if you're satisfied with using the maximum. Well, we are, because they said, can you make this dragster go with the best acceleration possible? So this equation will give you the best friction force you can get doing static friction. So, okay, it is fair. Now, how do I keep going with this question? The Fn happens to be the same size as the weight, right? It just is numerically equal to that. And now here's where I get super lucky, and the m's go away. They can be reduced, and I can plug and play and find out the acceleration. And so a quick calculation and this thing's done. But as I finish this off, I'm going to draw in a little picture of Scooby-Doo. So we can talk about Scooby-Doo, because we've all seen the cartoon and we've seen how Scooby-Doo gets around, right? How Scooby-Doo launches. And it does the funny little cartoon noise, right? Where it's like, and then Scooby-Doo runs away. Well, in the cartoon, if Scooby-Doo does that, if he spins his feet while he's trying to launch, then he's actually using sliding friction. That is not as good as static friction. Remember the last lesson, we saw the sliding friction number for the dog was like, I don't know, 44 newtons or something like that. Scooby-Doo would always be generating 44 newtons no matter how fast he spins his feet. But if he uses static friction based on last day's numbers, he could do anywhere from 0 to 58. So he could do a more gentle launch, or he could do an even more aggressive launch if he chooses. So that's why we want to not spin our tires, because you actually have the opportunity to have all different kinds of accelerations instead of just one, and you even have the opportunity for a bigger acceleration. Okay, same story but in reverse. This could be a car trying to stop, or let's change it up a little bit. Let's make it a crate on the bed of a truck, and we're trying to stop the truck without having the crate slide. So the truck bed's got a static coefficient of friction of 0.7. You're going down the road, oh, something comes out in the road in front of you, I don't know, some animal or something, so you try to stop the truck, and you don't want the crate to slide. Maybe it's not tethered down very well, and so you start stopping the truck. Well, free body diagram, we've got the weight of the crate going down. The bed of the truck will push up with the exact same size force in this story here. They're very different forces, but they happen to be numerically the same size. And then as you push the brakes of the truck and the truck starts to slow down, there is a tendency for the crate to shove the bed of the truck forward. Now, I'm not really worried about the truck, but what's neat is if a crate tries to shove the truck forward, Newton's third law says, oh yeah, then the bed of the truck will shove the crate backwards. And so this is how we actually stop cars. The car's brakes try to shove the pavement forward, and then the pavement shoves back on the car. Looking at the free body diagram of just the crate, don't worry about the truck, it'll be okay. I can see that the total force with the FG and the FN canceling is just a backwards FF. So when I go to do F net equals MA, I'm just going to say, yeah, let's put in FF. Negative if you wish, just to highlight that it's backwards. And since they've said, oh yeah, can you go best value possible, please? Like I know you can do gentle braking, but let's go best value possible. So we'll take the static friction right up to the max. And that is the only time the equation for friction actually gives you the right value for friction, for static friction, is if you're at the max. Well, we are, so it's good. Cancel the m's, throw in the numbers. This story's over. Negative 6.86 meters per second squared. Okay, a couple more examples to go. This one here, I don't know if you remember in Physics 11, we saw this video of one of our fellow Penticton teachers pulling gently on a cat that was not wanting to go for a walk. And the cat was just choosing to have itself get slid across the kitchen floor. And so let's kind of pretend that this is like that, although this would be an awfully heavy cat. So there's this box. It's 20 kilograms. And somebody's pulling on it with like a leash. But look how they're pulling. This 117 newtons is actually not sideways. It's actually at an angle, a 30-degree angle. And that's actually going to make this problem really interesting. There is a stickiness number there. It doesn't say what kind. I'll assume it's moving, right? If they don't tell me, I'm assuming it's a moving one. And they want us to find the final velocity after 3 meters. Okay, here goes. I'm going to draw a free body diagram. I could do it right on that picture if I thought there was some room. I'm just going to do it just down here a little bit. I think it fits on your page well too. Okay, 20 kilograms has a weight of almost 200, 196 actually. And if this was, Physics 11, we would have said, oh, hey, the normal force will be upwards, 196. Yeah, on simple stories, that's true, but it's actually different here. You see, this person, this human, is pulling with 117 newtons, and they're pulling at an angle. So they're actually pulling to the right and they're pulling up. They're helping to hold this box up from falling into the earth. So what I'm going to do is break that 117 up using the techniques we talked about a couple of days ago. If you want to know the x component, just use cosine. So 117 times the cosine of 30 is 101 newtons. I know they're pulling with 117 in real life, but I can say, hey, you're pulling with 101 to the side. And I know they're pulling with 117, but they're actually pulling up with 58.8. So as they pull the box to the side, they're almost sort of lifting the box off the ground. 58 won't do, right? Because the weight's 196, but they're trying. So the earth pulls down with 196, and they're pulling up with 58. That kitchen floor does not have to push up with 196. The normal force here will be actually only 137. I just subtracted the 58 off the 196. You see, with the 137 from the kitchen floor and the 58 from the person, that'll balance out the 196. But the neat thing is, this normal force, it's not 196, so the friction's been reduced by pulling up slightly. And speaking of friction, let's throw it in. It's sliding. So the equation works, right? This is a subtle but important issue. This equation works every time for sliding stories. But for stuck stories, like the previous 2 examples, be careful. The equation's only for maximums. But this is a sliding story, it'll be fine. So I'm going to go and put in my stickiness number of 0.2 and my normal force, which is not 196. And I see that the friction is 27. Okay, looking at this now, the 137 and the 58 cooperate to battle the 196. We don't have to talk about those ones anymore. And we're certainly not talking about the 117 because we're using the 101 and the 58 instead. So now I'm down to two forces, a 101 and a 27. Looks like they're having a little battle here. The 101's to the right, 27's to the left. I'm going to put that into F equals ma. Got 101 fighting 27. I just want to tell the physics the story. The net force, right, when I let the 101 battle against that 27, looks like it's 73. Now, backing up a little bit, notice nowhere in this picture do you see 73 newtons. The 73 is not real. It's just an idea. That picture's got the real stuff. This is just an idea that it's like 73. Okay, divide by the 20, got the acceleration. And now if you wanted to, you could go into your kinematic. Like all this stuff from here down, pretty darn boring. Okay, it's up to that 3.6 number that's cool. How we can actually break up that force, see a difference in the Fn, and then carefully calculate the friction and do F net equals ma. All right, so far so good. We're down to a final question, kind of a double question. It kind of mimics one in the textbook where there was this block of wood or something on a kitchen counter with a pulley and then a bucket where they were filling it with sand. And I thought, well, that's not very cool. Let's go with a dog instead of a block of wood. And instead of filling the bucket with sand, let's fill it with squirrels. So this dog is sitting there, just hold it, like belaying the bucket. And then we're going to start adding squirrels until finally the dog breaks free and starts to slide. So this page, top half of your note there, is all about breaking it free, getting to the point where the dog finally breaks free. So this top half of your page will be static. Let's get the free body diagram going. The dog has a weight, and then the kitchen counter pushes back up. Happens to be exactly the same size. We've already seen these numbers from the previous day. 15 kilograms, it's like 147. So 147 down, 147 up. Then the forces that line up in the direction of motion, as we would say, right? What's going on with forces that go this way, right? Because that's the way things are going to move. Well, let's go find out. We've got an mg down for the bucket of squirrels, and we're going to keep adding squirrels until it breaks free. So that mg is going to get bigger and bigger and bigger and bigger. There's a tension pulling up. That's the dog talking to the bucket saying, hey, bucket, don't go. That tension's going to get bigger and bigger and bigger as the squirrels start getting added, right? Because it has to match the mg. But if a dog pulls up on the squirrel's going to pull sideways on the dog. So as the dog tries to hold the squirrels, which become more numerous, the squirrels are going to be pulling harder and harder and harder on the dog. So we're going to be asking more and more and more from this stuck friction force. So those red forces are all equal. Maybe they start at like, I don't know, 4 newtons when one squirrel's in there, then 8 when there's 2, and then 12. And we just keep adding squirrels until finally all of those red numbers, which are all equal, finally they hit that do not exceed number for the dog's feet. Now, if you remember from last day, using this equation to find the maximum, and that's what you get from this equation for static friction, you get maximums. We saw this 58 number. So those red forces, they can be 4 newtons, they can be 12, they can be 30, they can be 40 newtons, they can be 55, but when we get to 58.8, that's when things are going to break free. Okay, so red forces are all 58.8. That means this tension here is 58. That means this mg is that 58.8. It looks like you have got 6 kilograms of squirrels sitting there in that. That's a lot of squirrels. When we hit that 6 kilograms, that's when it breaks free. And that's when you have to go to the next part of your notebook, right? You have to say, okay, all right, it's a do-over. New picture, new numbers. This thing's moving. And it's going to be moving with a bucket full of squirrels that have a weight of 58.8. But as soon as it breaks free, the dog's feet, which have been working up to this 58.8 newtons of friction, they're going to go, nope, boom, and it's going to drop down to that lower number, which I think we saw was 44. So basically the same picture, but with new numbers for the red stuff. We have 58.8 for the weight of the squirrels. And now let's go and figure out what's going on with every other part of this problem. All right, sliding friction. This equation always works for sliding, and yeah, it's 44. So that's too bad, but this friction force right here, it was scaling up to 58.8, and then instantly, as soon as the dog slides, it goes, I'm sorry, and it drops to 44.1. That's not good, because there's still 58.8 from these squirrels. So that's going to cause some acceleration here. All right. I don't know what the tension's going to be. It's going to be some number hiding in between the 44 and the 58. Let's try working with all of the story, the dog and the squirrels. Because if I do the dog and the squirrels, the two t's will cancel. One is forward and one is backward. And I don't even have to put them into my fnet story here. I don't have to bother going plus t minus t. So I've got 58.8 minus the 44. You got 14 extra newtons trying to get everybody going. And by everybody, I mean the 15 kilogram dog and the 6 kilograms of squirrels. That's where the 21 comes from. Okay, it's accelerating, not aggressively, but it is accelerating at 0.7 meters per second squared. Now let's go and take a look at one of the items. It doesn't matter which one, I'm going to pick the dog. For the dog, it's got a rope force forward. That's the squirrels talking to the dog, saying, come on, dog, let's go. And it's got its 44 newtons back. And it's going to make the dog accelerate at 0.7. And so there it is. We can see that the tension will actually be not 44, not 58, but it's at this number in the middle there, kind of in the middle, 54.6 newtons. And so that wraps up the lesson here where we were just reviewing kinematics and dynamics, bringing in some friction. And then next day we're going to take a look at what happens if you've got things tipped at an angle and we have some ramps. Okay, but this finishes up our friction.